Every 10 seconds, a train somewhere in the world crosses a line of steel, a path born from fire and precision. Before it carries passengers or freight, before it connects nations, this steel must first survive its own creation. At temperatures above 1,500 degrees Celsius, iron ore melts into a river of light. Carbon and manganese are added to stabilize its strength. In massive furnaces taller than buildings, oxygen burns away impurities. Each ton of metal refined to a controlled composition, density, hardness, carbon ratio, all measured, logged, and certified. As molten steel flows into molds, sparks scatter like stars, and motion begins. What starts as chaos will soon become geometry, and from that geometry, the line that moves the world. But before steel can carry motion, it must be born perfectly straight. Inside the blast furnace, raw materials transform into liquid metal. Iron ore, coke, and limestone descend through layers of heat exceeding 1,500 degrees Celsius. Air enriched with oxygen fuels continuous combustion pressure, 2.5 atmospheres, thermal efficiency over 90%. The molten iron flows downward into the crucible, separating slag from usable metal. Meters below, sensors track temperature and carbon saturation. Deviation beyond 0.2% triggers immediate feed adjustment. From the base of the furnace, liquid steel pours into ladles 300 tons each, guided toward the continuous casting line. As the stream solidifies, the sound shifts from a roar to a steady pulse. The process repeats, 24 hours a day, every day of the year. Steel has no night-only flow, refinement, and control. But molten steel alone cannot serve. To move the world, it must take form the geometry of endurance.
From optical sensor captures microtexture of molten steel. Robotic stirring rods churn the alloy to homogenize temperature.
From the casting line, red-hot steel blooms travel down conveyors at over 1 meter per second. Hydraulic shears trim edges before the rolling mills take over. Each roller compresses the metal with thousands of tons of force, stretching it into the classic eye-shaped profile, head, web, and base. At 1,000 degrees Celsius, the metal behaves like clay, under extreme pressure, flowing but never breaking. Automated sensors adjust roller gaps in real time, maintaining tolerance within plus or minus 0.3 millimeters. Over 20 consecutive rollers refine every curve until dimensions align to the blueprint. When the final stand releases the rail, it extends nearly 100 meters, glowing orange with energy that has become shape. Cooling air jets remove surface scale, leaving a uniform grain tight, dense, ready for strength. But perfect form is meaningless if it cannot remain straight. Next, the rail must face forces that will define its endurance for decades.
Extends hundreds of meters. Each section emits a mechanical pulse as rails pass.
As the hot rail leaves the mill, it enters the straightening line, a corridor of precision. Massive rollers, synchronized by computer control, exert equal pressure along the entire length. Sensors measure lateral deviation to 0.1 millimeters. Adjustments occur at 200 corrections per second. Thermal cameras track cooling uniformity. Uneven contraction can destroy alignment. Hydraulic rams stretch the rail slightly beyond its design length, then release it to stabilize internal stress. Each 100-meter section passes through laser scanners that verify its flatness and linear integrity. Operators observe through glass chambers, monitoring vibration graphs and digital overlays. From liquid chaos, the line is now precise, long, straight, and silent. But straightness is not enough. Where trains will travel, the rail must resist a lifetime of friction.
Flatness tolerance, 0.1 millimeters.
The rail's head, the surface that meets the train's wheels, is hardened by controlled heat treatment. Induction coils raise the temperature of the top layer to nearly 900 degrees Celsius, while the base remains cool. Immediately after, high-pressure water jets quench the heated zone, locking carbon structures into martensitic hardness. The process transforms the surface to resist wear while maintaining internal flexibility. Metallurgists monitor hardness profiles through ultrasonic feedback. Readouts show head 400 Brinell, web 300, base 250, a perfect gradient. What emerges is a material capable of enduring millions of wheel passes without deformation. The lifespan of a rail can now exceed 50 years, its memory recorded in every rotation. But endurance must be proven. The next stage reveals whether perfection can survive motion itself.
Head 400 HB, web 300 HB, base 250 HB.
After heat treatment, every rail enters a chamber of verification. Ultrasonic sensors scan the metal's interior for voids, inclusions, or cracks invisible to the eye. 32 probes emit high-frequency waves across the head and web, mapping reflections in real time. The data appears as moving lines on the monitor: amplitude, frequency, delay. A single anomaly triggers an alarm, and the section is marked for remelt. Next, mechanical test rigs apply vertical pressure exceeding 30 tons. Strain gauges record deflection within 0.02 millimeters. Thermal imaging cameras visualize friction zones during simulated wheel contact at 250 kilometers per hour. Only rails with zero subsurface error receive the certification stamp. Their geometry is no longer theory, it is survived proof. Perfection verified in stillness must now prove itself in motion. The journey begins with joining. In the welding hall, individual rails meet for the first time. Electric flash welding arcs across their ends, melting steel edges together. Pressure drives fusion until the joint cools into a seamless bond stronger than the metal around it. Each weld is ground flush to remove any elevation. Deviation must stay below 0.1 millimeter. Ultrasonic inspection confirms the joint's internal continuity. Cranes lift completed lines 400 meters long onto transport cars. Chains tighten, vibration dampers lock, and the convoy begins its slow departure toward the construction site. Through every meter of track, geometry repeats, connecting distances once measured in weeks into seconds. But the process never ends here. What began in fire now moves across continents, carrying the weight of civilization itself. Across deserts, mountains, and cities, every train that moves today rides on steel forged in precision. Beneath each wheel lies a century of metallurgy, calibration, and endurance. The rail does not rest. Day and night, it expands and contracts, carrying vibration, load, and time itself. From molten metal to endless motion, nothing in this process is random. Every micron measured, every surface tested. The world moves because the line holds. It endures heat, friction, pressure, and weather, quietly maintaining the geometry that keeps civilization aligned. Precision forged in steel, the foundation of every journey. Subscribe to 360 Global Process to witness how the world keeps moving.